All right, look like I'm going live. Got the right stuff all hooked in here. So let's go ahead and start this video here.
You remember one about that kind of topic?
All right. So I wanted to do differential equations and also set up for mixing problem.
I never put you under that bus.
So
Sure,
let's see. I got
That's a full
myself up
responsibility.
here.
Yeah. Show your real prince.
Current viewers. All right, look, I got something going on. So let's go ahead and get this going here.
Hey. Remember that foreclosure we served a couple months back? The missing girl, Vera? You said you'd looked into her old roommate's phone records?
Okay.
Found an address
So let's see.
where
So
she was called from?
before I do, let's go ahead and go to a little bit of background, get everything set up. All right. Let me put this in, change over to this pad.
Help me out with this, and I promise to do a fearless sense searching of inventory.
All right, so when we talk about mixing problems, what we're talking about is system changes, so a linear system. So in cases where there is, let me get this here. Let me point you to the, all right, so in cases where there is a system with one variable is subject to a constant change, it's important to be able to model the rate of change. All right, so the system has to be described in terms of a variable of interest and a time. So if we look at this whole mixing problem, that's what we're talking about here. We're talking about, the change within the tank itself, and we're going to have an input and an output. And when we look at it, in order to understand the changes, we have to understand both what's going into the system and what is coming out of the system. And really, when we think about this differential equation that we're going to have to develop for this, that is ultimately what we're trying to do, is understand what that input and that output is. Now, the input itself is actually fairly easy, but we're going to have to also look at what the output is. Alrighty, now when we look at a system like this mixing problem, when we represent what that input and output is, we can do it in several ways. We can look at it in terms of just a concentration. We can look at it as a percentage, but ultimately we're looking at, changes, the ingredient amount. All right, so let's go ahead and use a little bit more of a better visual here. Here we have the input, or the output, and there's a few things we can kind of set up as just an understanding for what's going on here. One, we're looking at a specific type of situation where there's a constant flow rate. So the volume stays constant. So that means the input and the output are going to be equal. So it's going to be the same flow rate coming between the tank. That means that our volume is going to be constant. We're also going to assume the tank is well mixed. It's a perfect mixture, no settling at the bottom, no floating at the top. Concentrations even throughout. The fluid is going in is known. We already figured what the fluid going in was, and the level of concentration within the tank is going to be constantly changing. So whatever's coming into this tank, again, it's a known, and what's going on in this tank is constantly changing, meaning that there's some sort of, obviously some sort of mixing is happening, that this may have not been a consistent volume or a consistent amount. There's some difference between the two. So that means that our differential equation is going to be this. The change in the tank is going to equal the difference between the rate of what that concentration going in minus the rate that the concentration is also leaving that tank. So the rate going out is in constant change as well. Alrighty. Alright. So again, so this comes into the question of what do we want to know, and what is the amount of substance at any time t. So the concentration at any given time, change in the tank is the difference between the input and the output, and we can go ahead and represent what's going on in that tank as as a differential. The differential of the substance with respect to time. Lincoln, that's setting up a differential equation. We can talk about what's going into the tank. You get the known volumetric flow rate. So we got a known flow rate. In this case, gallons per minute. This could also be liters per minute. Ounces per second. So some sort of flow, volumetric volume, and a unit of time times whatever the concentration is. The substance per unit gallon or unit of liquid. In this case, gallons, but again, that could also be liters. And then the product of those gives us the amount of that substance that's coming in at a rate of time. Another way to look at this, if you think about this mathematically, your units would cancel out, leaving you with whatever unit you're measuring that substance is per rate of time. So what we've done, again, per the differential equation, we're putting this in the substance going in at a time. So keep in, this is what we're talking about going in. So the rate going in, so unit, and then change in tank is substance with respect to time. So our units do match. Now how are we going to describe what's going out? Remember, that is not known, and that is constantly changing. So what's going out of the tank, you can look at that through these terms. So what's going out, again, is still going to be a flow rate, but we've got a changing rate of the concentration, per the unit in the tank. So whatever this volume is, when this starts out, there's some amount of substance per the volume. Per unit volume. So what we have is the flow rate. Again, gallons per minute, then equal to the flow rate going in, times whatever that substance per the tank's volume. So if we look at this tank, and now we're going to put it just in terms of variables. We're going to have Q as the flow rate, C is going to equal concentration, and V is going to be the volume of the tank. So again, we got what's going on in the tank, the rate of change of the substance with respect to time. We got a function for finding out what's going into the tank, the flow rate times concentration is equal to the substance per minute. So that comes in and what's going out is the flow rate times the substance per unit volume of the tank itself. So if we look at this in terms of an equation, you can write this a little bit more. The differential is the substance per minute minus the flow rate per the volume of the tank times whatever amount of times the substance at any time t. So we can write it a little more succinctly, just like this. So this is just a way of writing it so that it looks a little bit more consistent with a equation or a formula that you can use. So your substance with respect to time is equal to the concentration times the flow rate going in minus the flow rate of what's going out per the volume of the tank times this unknown substance, which is going to be changing from any amount of time going out. If we write that out, this comes out as a first order linear differential equation. It's just not written in standard form at this point. So what we got here is, just just written. It's not in standard form. But what we have, is the first order linear differential equation. We got the differential. Here we got p of x times y. Y is the variable that we're trying to figure out, which is the same as the substance. And then we got this f of x, which would be analogous to the what's going in. We add this to both sides, and now we're getting more like a differential equation, or the first order linear differential equation. And here you can see those parallels. P of x is the flow rate over the volume. F of x is the same as the rate going in. Y is the same as what that substance is constantly changing. And dy over dt is just the rate of change of substance with respect to time. So when we look at this, let's look at this in terms of a problem. This is really the reason everybody came here, or that we're looking at this video. So what we have is, the problem. A tank is filled with solution made up of sugar water. All right. The sugar water, is used as part of a sweetener station for a beverage company. The amount of sugar in the tank determines one product from another. Okay, so you got this tank that is basically the only fill station to make some sort of soda. They change the amount of sugar in the tank, and depending on the sugar level, they call it one substance, or substance A or substance B or C or D, depending on the level of sugar required. So during a changeover, the tank doesn't get completely drained, and instead of a syrup, a higher concentration of sugar water is pumped into the tank at a particular rate, while solution is pumped from the tank at an equal rate and sent off to storage. So they just don't want to waste it. They're going to use that material again. So the volume of the liquid doesn't change. So we'll just set this up so it's basically like our problem. So it's got a flow rate going in is equal to the flow rate going out. You also know what's going in has a higher concentration of sugar. So you got this tank that is going in the constant state of change until it reaches some preset concentration of sugar again. So if we write this out a little more concise, you got the 100-gallon tank. You got 10 pounds of sugar in solution. And what's going in is a syrup made of 1 pound of sugar per gallon, and is pumped at a rate of 2 gallons per minute. And what's going out is the mixed solution going out at 2 gallons per minute. So determine the differential equation that describes the concentration of sugar in the tank at any point in time t. All right. So you got, if we just look at this video here, this picture there, you've got a concentration going in, and then you've got something coming out. And here, this is a 100-gallon tank. And in this tank, you've got 10 pounds of sugar, and this concentration is 1 pound of sugar per gallon of water. It's going at a rate of 2 gallons per minute. And so the only thing we know here is that whatever is in this fluid is leaving at 2 gallons per minute. So we don't know exactly what's going in or out yet. So if we just write this out a little bit different, again, trying to just drive this home a little bit in a different format, what you have is just the same information, just writing it in a little bit easier way to see. So you get the syrup, 1 pound of gallon of sugar per gallon, 1 pound of sugar per gallon of water, and is pumped at 2 gallons per minute. So if we put this just in terms of the sugar, we want to know how that sugar is changing, because again, we don't really care about the water, we just want to know how much sugar is in it. So we put this all in terms of sugar. So you got how much sugar goes in per minute is equal to the flow rate, which is 2 gallons per minute, times sugar per gallon, 1 sugar per gallon, 1 pound of sugar per gallon. And this will break down like we saw on the first slide. That'll give us pounds of sugar going in per minute. So if we write it out this way, 2 gallons per minute times 1 pound of sugar per gallon, gallons cancel, and then that tells us there is 2 pounds of sugar for every minute. So and this is our rate of sugar going in.
What's the real purpose?
2 pounds per minute. Now if we consider what's going out, we know it's 2 gallons per minute going out because we got constant volume. Now to get the idea of the concentration, you've got a 100-gallon tank. The concentration of the sugar is gradually increasing, or the rich syrup is going into the tank, so it's gradually increasing, but the flow rate out is the same as the flow rate in. So, and we don't know exactly what's going on because it's constantly changing. So we can write that getting sugar out per minute will make the sugar into a variable at any time t. It's 2 gallons per minute in 100 gallons. So what we end up with is 1 over 50, or 2 over 100 pounds per sugar per minute. And here we got 1 over 50 sugar at any times t. That's going to represent what's going out. So we got this 150 as a constant, and this times sugar at any times t is the variable. So you can see how this is going to turn into a p. This is representing p of x, or in this case, it'll probably be called p of t. And this is the variable that we're going to have to learn what that ultimately is at any given time. And this is important to keep remembering. You're worried about any given time. So the rate of change of sugar in the tank is equal to the difference in the rate that the sugar enters and the rate the sugar leaves at any point in time. All right, so let's walk through this a little bit more. So again, that looks familiar, what we were saying as far as how to, we're going to set up the differential equation. So if we look at it in terms of the rate of sugar at any time t is going to equal to the rate of the sugar in, which is 2 pounds of sugar per minute, minus your sugar, whatever that variable t is going out, which is constantly changing. This is a function of time, t. Then per 100 gallons times 2 gallons per minute. Again, so now this is what we can use. It can be reduced a bit to describe the rate of change of the sugar. So we solve the differential equation, and this puts it into standard form. So the rate of change of sugar at time t plus the sugar at time t over 50 minutes is equal to 2 pounds of sugar per minute. So you can see this is in a standard form, dy over dx. Over there. Here we got this function of x is 2 pounds of sugar per minute. And then we've got this function here of sugar t, and 1 over 50 is our p of x. All right, so now that's our, again, showing these relationships a little bit easier. So now you can start seeing how this is just, a first order linear differential equation. Setting these problems is the hardest part, is getting them in order. So in order to solve this, we're going to need the integrating factor. So that's e raised to the infinite sum of p of x dx.
I can't see that being of any interest. A waste removal service poisons park farmland.
So we got our integrating factor,
A major
and our p of x, or in this case we're calling it p of t, is 1 over 50. Our f of t is going to be 2. So if we multiply times this original differential equation, this is what we do with the integrating factor. Or excuse me, I missed a line here. Our integrating factor is e raised to the infinite sum of p of t dt, and that comes out to e raised to the infinite sum of dt over 50, which equals e raised to t over 50. So now we got this integrating factor. Multiply the integrating factor through this equation. So what we end up with is, here this represents the product rule, and this is just the integrating factor times f of x. Now the whole purpose of that integrating factor is to undo that product rule. All right, so if we look at the undoing of the product rule, here we have the integrating factor times the sugar density times t, and up here this represents the fact that this is a derivative. That's a derivative. Now, and this is just the product of 2 times the integrating factor. So if we take the antiderivative of both sides of this equation, all that's going to do is undo this and just leave us with the argument of the integrating factor times the sugar at time t. So we integrate both sides. On the left side, all we're doing is these just cancel. On the right side, our 2 comes outside the infinite sum. It's a constant. Now to integrate e to the base, or by base e, that comes out, but then you also multiply by this 50. So we end up with 100 times e over t over 50 plus c, or e raised to the t over 50 plus c, constant of integration. All right, almost done. Now let's see, we have to solve for the amount of sugar at any time t. This is going to make it look more like a function that you're used to. Sorry about that. Alrighty. So you get the sugar at any time t is equal to 100. C cancels, and C, the constant of integration times e raised to the negative t over 50. Now that's just a general solution. We do have an initial condition. We knew how much sugar was in that tank at time 0, and when this goes to 0, this goes to 1. This sets equal to the initial amount of sugar that was in the tank, and we can solve for c. So that means that time 0, there was 10 pounds of sugar in the tank, and since that goes to 1, that lets us know that c is negative 90. 10 minus 100. Now here we actually have a model that can figure out how much sugar is in that tank at any given time. Oh, and this was just the rule of using the by taking the infinite sum or antiderivative of something to base e. 50 just represents a. So divide by 1 over 50 is just multiplying by 50, which gives you that 100. Now, if we take that model, we put it into an Excel file, which is what I did earlier, and just plugged in a time t, for from 0 to 12 minutes. You can actually see what's going on with that sugar in the tank. It's gradually increasing over time, but it's not a linear relationship. You'll see the first step was going up 1.8, then went up to 13.5, 15.2. So it wasn't a consistent amount. It really did need to be modeled. So what we can do is look at see. It started off at time 0 at 10 pounds, and over the course of 12 minutes, I think I only got it up to here, which is like 10 minutes, which is just a little more than 25, so 26.3 at this point. So that was just the mixing problem I wanted to go through here. And let's see here. I was also going to, the benefit of doing this on a live stream is just on seeing if there's any particular, feedback that I could get. So we got Chris, differential equations are so beautiful. Sorry, I had to take my deal down so I could see this. Yeah, they're pretty neat. Something that you could get some use out of, kind of understand them a little bit, be able to put some use to them. Hopefully that you got that out of that as well. So I'll do these periodically. I like doing this live stream, being able to get feedback. Also being able to get some questions, from people who may need to help some understanding, differential equations. So it can kind of be a little helpful to others. So if there are no other questions, then I will go. So this is Professor Cummings, just tuning in for people to get a little bit of insight. And I'll talk to you later.